So are able to see this? See, this is what in the last class that we looked at, lecture number 27. You see that we started with understanding these terms: center of gravity, center of mass, and centroid. And this diagram on my right is what is representing. That is this diagram. So individual weights, discretized weight W1, W2 up to Wn, their moments about x-axis or their moment about y-axis or z-axis are going to be summation of the total weight moment about those respective axes. That's why Warrington's theorem. So that if you use, you would represent there can be three scalar equations defining x bar, y bar, z bar, which is centroid of the rigid body, and that is what is changed to two scalar equation and one scalar equation, and so on, that we have seen. And importantly, this definition of axis of symmetry, center of symmetry, and plane of symmetry that you have understood, so that readily you are able to look at the standard section and find the centroidal location without having this first moment principle applied. However, for some examples like isosceles triangle here, look at. So this 1/3 of height cannot be obtained just by observation. So you have to use first moment principle. Like for example, you take a cone. So you know by axis of symmetry, I know that centroid is along the axis of the cone, but you require to find out this y bar, which is equal to h by 3 through a moment of volume about the other xy plane, xz plane. So this is what you understood from this plane of symmetry and so on. So if I have two plane of symmetry, I could locate my centroid. If I have two axes of symmetry, I could locate my centroid in a plane like that. So you also have understood what do you mean by center of symmetry. So if we have a section in first and third quadrant, opposite quadrant, that means the point in first quadrant area x comma y, if I take, I will have a corresponding point minus x comma minus y on the other side. Then you see that the first moment of the first quadrant area and first moment of the third quadrant area about the same axis would be 0. So you would be able to get your center of symmetry so that you would locate your centroid. Whereas on the other hand, you have this T section. So this T section you can have axis of symmetry, but on this axis of symmetry, where is that centroid located? You should find out. Maybe you require a base reference this, and from here how much above it is located, that you require to find. So these all are the understanding that from the last class that we had. We also have looked at how these formulas are come from this first moment of area definition, Qx and Qy, right? This is clearly explained in last class, and also had a sample explanation of how do you get centroid for a triangle, right angle triangle, through the definition of first moment principle, right? And we extended that for a circle as well. Semicircle, when you take, you know that axis of symmetry is YC axis, but on YC axis from the diameter, how much it is above, that's y bar to get, which is equal to 4r by 3 pi. I should use this first moment of my semicircle about x-axis that I should find out. So what is that I have got here is the first moment about x-axis, Qx. So that Qx is going to be a into y bar. That's going to be integral y dA. So this is what I have used to find my y bar, right? So this is how you can understand. So our task is not to derive this. Of course, you can look at the textbook. For every standard geometry, you have such a application of first moment principle to locate centroid, and readily formulas are given with respect to the given reference. That you should remember, because you may have a section of a rigid body of composite section. What I mean by composite section, you can have a section not a regular rectangle or a triangle or a circle. The combination of these regular geometries added or subtracted from one the other. So you will have a section, and such sections are called composite section. If that is so, how do you locate your centroid is what is the question mark, and that to solve you require a set of formulas derived from this first moment principle. Right. So let me just give you the list of formulas and then solve one problem. Then we'll go into second moment of area. Why does it require and so on to see. Okay, so this is what we did in the last class. So today's lecture number 28. And today's date is 12/04/2021. So it is now centroid of title of today's class is centroid of composite areas. So how do you determine? So beforehand, let us just list down these formulas, right? So let me put serial number. So as I explain you here, put down these formulas. Please write down in your notebook parallelly. Geometry, and what is the area of that standard geometry. So if geometry dimension is given, individual dimension is given in mm, so these all are in mm square area, right? And what is x bar? And what is y bar? So let us get this for some standard geometry. So number one, a rectangular geometry, rectangular section. So if this rectangle dimension is b and depth d, and this is described with respect to reference axis set x and y, and this is my origin O. So now with respect to this point origin, where is the centroid is located for this rectangle can be obtained by observation itself. Of course, you can apply the first moment principle, but here since this rectangle has got two axes of symmetry, one is this, another one is this, and I call this axis as yc and xc axis, and they are located at a distance b by 2. So x bar is b by 2 and y bar is d by 2, and the area of the triangle is length into width, so it's BD. So this is very straightforward, that you know very well, right? So this is first formula. What is my second formula? So let us look at the second one is for a triangle. So if I take an unequal triangle, something like this. If I take a triangle, something like this. So this is my base. And in this base, I see from base midpoint to the vertex, opposite vertex, what is this is called median. So I know on median I will have my centroid, and that would act if this is of height h, this triangle is of height h. It's not median length h, it is height from base to this vertical distance. And now the formula of triangle is half into b into h area, and the centroid x bar to get, I should have some reference. So let me take this entire triangle as represented like x, y, and this is my origin O. Then with respect to this, where is that located is on median. Because median is that one point which connects the vertex to the midpoint of the base. On median it is there, but how much it is along this is y bar, that is h by 3. So you can prove this, but we will not go for this now. We'll have to just remember these formulas. So this is for this. So if I have a geometry which is a right angle triangle, what we have seen already in the last class, so you know how these formulas are obtained. So I would have my centroidal axis. One is this, other one is this. with respect to the reference axis x comma y, holding this as origin, I can write my surface area now is half into b into h, where b is base and h is height of the triangle. And what is my x bar is now from O, where is this axis located? So this distance is what is my x bar. So that is b by 3. And this height is what is my y bar, that is h by 3. Right? So this you should remember. So if we continue like that, let us add some more sections, standard sections. So let me extend this line. So let's look at formula for the circle. So if I have my circle represented, it is very simple that by the axis of symmetry itself I could locate my centroid is center of the circle. And but you have to refer with respect to some reference, right? So if my reference is x comma y, and this point is O, now my if this is of circular area of radius r, then the area is pi r squared, you know. And what is the x bar? X bar is the centroidal axis distance from y axis. So this is yc axis and this is xc axis. So this distance is what is x bar and this distance is what is y bar. So that's happened to be r and r in this case, right? So every section should be defined its centroid with respect to a reference axis state, with respect to origin. That's important, right? So let us extend this further. And we just looked at for these 4 sections. So 5th section is that one what we have seen in the last class, semicircular section. So I have semicircular area and where this is x and this is y. And by observation I have one axis of symmetry. So I know in this my centroid is lying, but the other axis, this height is to be determined that we have done in the last class, which is y bar. And again this is of radius r. Then you know the surface area of this is pi r squared by 2, half the circle area. And now x bar is from here. Where is it located? That's x bar. That distance is r radius. And the other one is 4r by 3 pi, which we had derived in the last class. Right? So you should remember this. Again, if I have instead of semicircle a quarter circle, and that is defined with the xy axis set, holding this point as origin, my centroidal axis of the section would go through centroid, this yc and xc. And now the area value is 1/4 of circle area. And where are my centroid located is from here it is x bar, from here it is y bar. So x bar and y bar equal, and that is equal to 4r by 3 pi. 4r by 3 pi. So instead of surface area, if I have a wire, one-dimensional figure, then what would happen? What is the change? So let me put that same here itself, right? So instead of area, I consider a curve or a line. In such case, what is my thing? So if I take this quarter circular area instead of that, a wire bent into a quarter circular shape. So this is now with respect to this radius r, and this is point O, and this is x-axis and this is y-axis. Then here instead of area, I will write length of the wire. So what is the total length? Total length is, if it is happen to be circle, it is circumference of the circle 2 pi r, but it is quarter circle, so 2 pi r by 4. So it is pi r by 2 is the length. and the centroidal locations are going to be different. So these are my centroidal axis. So that's not lying on the physical geometry. It is outside. So this is YC, this is XC. And you get your XC value. You can do this simple derivation. I'm not going to do, but you remember now what is X bar value. This distance is given by 2r by pi, 2r by pi. And this distance Y bar is given by 2r by pi. So one can define that simply by taking an elemental length of at an angle theta, and then you can do xy coordinate in terms of sin theta, cos theta. You will be able to derive this expression, right, from this first principle. So what is x bar? It is integral x dl by dl. Y bar is integral y dl by integral dl. So using this you can derive this formula. I leave it to you as a homework to verify. And this is all that you should remember, right? So if you remember this, you can now go for solving a problem. So I will just explain you solving a problem. Find out a centroid of this shown composite area, right?